So on to the next learning objective. Again, the second number here is changed. Now we're kind of getting away from inverse trig, and we're going to be relating things to solving equations again. All right, 1.11 was about solving equations, so all this is related to that. All right, now we're going to be using the help of our identities that we learned in 1.21 and 1.22 to help us. So now we have some extra kind of formulas floating around. All right, so you might need to look at those prior to kind of going through these examples. All right, so that's basically what I just said. We learned the sum, difference, and double angle identities. All right, so we're going to use those to help us solve equations. All right, there's also one more that's not in the sum, difference, and double angle identities that we use quite often. That's the very first one that we learned. All right, so make sure you add this one called the fundamental identity to that list. All right, you have your sum ones, your different ones, and your double angle identities, all right, as well as this one. All right, so we're going to solve this one. This problem looks really, really complicated. We have cosine of 4x mixed with the cosine. We have a sine of 4x mixed with a sine, and that's all equal to 1/2. And it looks really complicated, but if you have your list of identities, you see we kind of have this pattern. We have these two cosines followed by these two sines, and then things in parentheses are the same. And if you look at those identities and kind of see what's similar, if we look at cosine of a minus b, it follows the exact same pattern. We have cosine of the first angle times cosine of the second angle, and then we add sine of the first angle, sine of the second angle. So this whole left-hand side is actually just following the same pattern as cosine of a minus b. So we're going to rewrite the left-hand side of cosine. The first angle is 4x. The second angle is x. And I can simplify inside the parentheses pretty nicely. I just get cosine of 3x equals 1/2. So using my sum and difference identities, I can simplify that left-hand side to something that's much simpler looking, especially when it comes to solving. Because if I look at this equation, this is exactly, let me check the numbers. This is exactly learning objective 1.12. So how did we do that? We call this U. And then this is exactly learning objective 1.11. Now we get our answers for U. See, cosine is 1/2 at pi over 3 plus 2 pi k. And it's also positive in quadrant 4. That's going to be 5 pi over 3 plus 2 pi k. All right, and all that was just from learning objective 1.11, figuring out how to find those angles. But now remember, this is actually 3x. So to finalize our answer, we have to multiply both sides by 1/3. All right, also divide by 3, but I just like to keep it as a fraction so we can combine it with the other fractions a little bit easier. And we get x equals pi over 9 plus 2 pi over 3k and 5 pi over 9 plus 2 pi over 3k. That's really the only new thing in this specific example is rewriting the really complicated looking expression up here, comparing that to our sum and difference identities and saying, hey, that follows the exact same pattern as cosine of a minus b, rewriting it and simplifying a bit. And then again, when we get to this red box in the middle, that's kind of going back to our previous learning objective. All right, if you did 1.12, you've known how to do these before. Again, it might be a little refresher, but you've done this problem before. And so go ahead and solve this problem. Again, keep in mind the types of identities that can help simplify. And here is the solution I came up with. So this follows the exact same pattern as the one in the previous. So again, we're using the cosine difference identity. So we're going to take 2x and subtract x. That actually simplifies really nicely, just a single x. So this is just learning objective 1.11. We don't have to do anything else. And we get these answers down here. All right, so now our next example, I have sine squared equals cosine squared. All right, when is this going to happen? This one, it's actually possible to kind of just reason through and not use any algebra, but I'll show how to do it using algebra. So the first thing is, whenever you're dealing with exponents, a lot of times you want to get 0 on one side. I'm going to subtract cosine squared to the other side. And at the very beginning of this video, I listed an extra identity, that's sine squared plus cosine squared equals 1. All right, we have a minus sign here, so it's not the exact identity, but what I can do is if I subtract sine squared to the other side, I can rewrite cosine squared using sine squared. So I'm going to do that now. Sine squared x minus, and whenever I'm plugging something in, I have to use parentheses because that negative is going to distribute. Minus 1 plus sine squared of x. And that's sines combined, 2 sine squared of x minus 1 equals 0. And then this equation, now that we've kind of got it into a point, the reason I did this, because this equation is really difficult because there's sines and cosines being mixed together. But in this equation, I just have sine. And this equation is going to be similar to learning objective 1.13, where I want to get it to the point where it's just sine by itself equals a number. So I'm going to do that is add 1 to both sides first. Divide both sides by 2. Take the square root of both sides. That finally gets me my sine all by itself because the square root of something squared cancels out. On the right hand side, whenever you take the square root of both sides in an equation, I have to get plus or minus the square root of 1/2. And we've actually seen the square root of 1/2 before, even though it doesn't look similar, but I can split up square roots over division. And I can multiply the top and bottom of this fraction by the square root of 2. And that looks more similar to something we've seen before, plus or minus the square root of 2. So now the final question is, when is sine of x equal to the positive or negative square root of 2 over 2? I'm going to write them over here. There's a lot of different answers. The first time it's positive square root of 2 over 2 is pi over 4. And then at 3 pi over 4 in quadrant 2. In quadrant 3, there's going to be a negative value at 5 pi over 4. And another negative value at 7 pi over 4 in quadrant 4. And I'm going to be a little lazy, but every single one of these you have to put a plus 2 pi k after. So again, kind of fiddling around with our identities. The only reason I kind of knew to use an identity in this case is because this equation here has multiple trig functions in it. And there's multiple trig functions, not a nice way to rewrite it as just a trig function equals a number. So I can get rid of one of these trig functions using this identity in the top right. And then from there, it's just kind of simplifying and figuring out what angles make this true. All right, so 6, cosecant times sine minus 2 sine equals 0. Well, now we're throwing in kind of some older trig functions. I didn't mention these at the beginning of the video, but we have a bunch of ways that cosecant, cotangent, tangent, secant are all related to the original sine and cosine. And it turns out that cosecant is just 1 over sine. So when we first learned this type of thing, we saw that it's really helpful to rewrite things in terms of sine and cosine, because then nice things like this will happen where we get some stuff to cancel out. So just remember that cosecant is related to 1 over sine. I get that first part of this equation just turned into 1. And again, this is probably an exact equation or something similar to the equation you solved in learning objective 1.13. I subtract 1 from both sides, divide by negative 2, and then figure out when is sine going to be 1/2. Sine is going to be 1/2 at pi over 6, and it's going to be positive at 5 pi over 6 in quadrant 2. All right, so that's how you would solve this one. Again, just remembering that cosecant is 1 over sine. And after that, it's really similar to problems you've solved before. All right, again, to finish up, what are the solutions to sine squared of x plus cosine squared of x equals 1? All right, so think about those identities that we used. What values would make this true?